Good morning, students. Myself, Kedarnath Vi, lecturer at AAA Department, Government Polytechnic, Raichur, from the Department of Collegiate and Technical Education, Bangalore. In this session, I will be discussing a few parts of digital principles from Unit 2 of subject Digital Electronics. I wholeheartedly welcome you all for this session. So here, I will be discussing total 5 topics. In the first topic, decimal number to binary number conversion. Second topic is conversion from decimal number system to fractional number system. Conversion from decimal number system to hexadecimal number system. Conversion from fractional decimal number to fractional decimal number system. And lastly, multiple choice questions. So here, integer conversion, fractional conversion, integer decimal conversion, and fractional decimal conversion. Decimal to binary conversion. The given number will be in decimal form. That number we need to convert to binary number. Okay, so a decimal as a base 10 and a binary as a base 2. So in any conversion, suppose if you are converting a decimal number to its equivalent binary, the base of that number changes to 2. All the decimal numbers can be written to its equivalent binary number. Any decimal number we can convert it to its equivalent 4-bit binary. So here, what is the necessity of conversion? Okay, so why we are converting a decimal to binary? So if you take computer applications, in computer application, which number system is used? So binary number system is used in computer applications. So what is the purpose of usage? So binary number system is used for programming purposes, or it is used for coding purposes, because a computer can understand a program or a code written in the form of binary digits, that is zeros and ones. So therefore, so we are converting a decimal number to binary for different computer applications, that is for coding purpose or programming purposes, because computer can understand only a programs or digits written in the binary digits, that is zeros and ones. So when you give input decimal number to a computer, so there will be inner conversion. The decimal number is again converted to binary, and the required operation will be performed, and finally the decimal number is again finally the binary number is again converted to decimal number. In this slide, a conversion from decimal to binary. So in the first column, it shows the decimal number, and the second column shows a binary equivalent of the given decimal number. So here decimal numbers 0 to 9. So here in the second column, the 4-bit equivalent of decimal number is written. Okay, so written using 8421 code. So first LSB is 2 power 0, 2 power 1, 2 square, and 2 cube. So therefore 2 power 0 is 1. So 2 power 1 is 2, 2 square is 4, and 2 cube is 8. So therefore I write here 8, 4, 2, 1 like this. Suppose you want here 2. Okay, 2 is the decimal number. So how to convert decimal number to binary in shortcut? So here this is the 2 power 0, that is 2 power 1, that is 2. So here 3 means 2 plus 1. So put 1 in 2th place and 1 in 0th place, that is 2 plus 1 is 3. Okay, so this slide is the conversion from decimal to binary. So in this slide, I will be see this decimal number means it contains integer part as well as fractional part. So this slide I am converting only a integer decimal number to its integer binary. Okay, so very clearly I am saying here I am taking a integer decimal number. I am converting it into integer binary. Okay, the required base is binary. The given base is decimal number. Which decimal number it is given? A decimal number containing integer part. So a decimal number containing integer part. For this, the procedure what we are using is successful division method by the required base. The required base is 2. So here I will be using 4 steps. Step number 1, step number 2, step number 3 and step number 4. So in step number 1, so the remainder obtained in step number 1 will be the LSB of required binary number. The remainder obtained in step number 4 will be the MSB of the required binary number. So let me see in detail stepwise. So divide the given decimal number by 2 successfully, where it gives the quotient along with the remainder. The remainder obtained here is the LSB of binary number. So in step in step 1, you have to take the given decimal number. The given decimal number is divided by 2 for the first time. When you divide the given decimal number by 2, we get 2 parameters. Number 1, quotient, and second one is remainder. The remainder obtained in the step number 1 will be the LSB of the binary number. Okay, the quotient obtained from step number 1 is taken in the step number 2. Okay, so divide the quotient obtained from step number 1 and the remainder obtained is the second LSB of the binary number. So here in step number 2, what we have taken, we have to take the quotient obtained in step number 1 and again you have to divide it by 2. Again we get quotient and remainder. The remainder in the step number 2 will be the second LSB of the binary number. Okay, so you have to repeat the same process until the quotient becomes 0 or further division is not possible. You have to consider the last remainder because further division is not possible. Same thing I have written here. Repeat the process till the quotient becomes 0 and the last remainder is the MSB of the binary number. So this is very important point. The last remainder will be the most significant bit of the binary number. So next is arrange all the remainders from MSB to LSB, which will give the required binary number. Okay, so this is the procedure for successive division method. Very simple. Step number 1, take the given decimal number, divide by 2, you will get the quotient and remainder. The remainder obtained is the first LSB of the required binary number. In step number 2, you take the quotient of step number 1, again divide it by 2, again you will get quotient and remainder. The remainder in step number 2 will be the second LSB of binary number. Okay, so you go to step number 3, you take the quotient of step number 2, again divide by 2, again you get the remainder and quotient. The remainder will be the third LSB of the required binary number. Okay, you have to repeat same steps you have to repeat. Up to what stage you have to repeat? Until the remainder becomes 0. Once the remainder becomes 0, you start writing the bits from MSB to LSB. Or another stage you will reach, further division is not possible. Up to that stage, you have to repeat the division. So let us take one example. 294 is the given decimal number. That number I am dividing with 2. So if you take the 294, if you divide by 2, so you will get quotient how much? 147. 147 you will get the quotient. Okay, so 294 divided by 2, quotient is 147. So what is the remainder? Remainder is 0. So what? So here remainder is 0. Binary value means binary. The same remainder I am taking it as binary value. The first remainder is the LSB of the required binary number. Okay. So again you take the quotient. This is the quotient obtained from first step. 147. 147 divided by 2. Quotient is how much? 73. So remainder is 1. What is the binary value? The same remainder, that is 1. Again you take the quotient of step number 2 in step number 3. 73 divided by 2 is how much? Quotient is 36. 36. Remainder is 1. Binary value is again same remainder 1. So say you have to repeat the steps. 36 divided by 2, quotient is 18, remainder is 0, binary value is 0. Then 18 divided by 2, quotient is 9, remainder is 0, binary value is 0. 9 divided by 2, quotient is 4, remainder is 1 and binary value is 1. 4 divided by 2, quotient is 2, remainder is 0, binary value is 0. 2 divided by 2, quotient is 1, remainder is 0 and binary value is 0. 1 divided by 2, quotient is 0. See here, you can see here. So quotient is 1. You have taken 1. Quotient 1 in the last step. Further division is not possible. Therefore, remainder is 1. So binary value is 1. So you have to write from what? From MSB to LSB. So you have to write in the reverse order. So first you have to write 1 0 0 1 0 0 1 1. So like this. Okay. So 294 is the decimal number. So 1, this is the MSB. 1 0 0 1 0 0 1 1 0. So here 1 0 0 1 0 0 1 1. Okay. So this is the conversion of integer decimal to integer binary. The same thing it is explained here. See here. So finally you should write like this. This is the MSB bit and this is the LSB bit. You start writing the binary digits in this way. If you write, see I have shown here arrow MSB towards LSB. You write the required answer as 1 0 0 1 0 0 1 1 0. So here this is the example which contains the decimal number. So here this is the example 2 of converting a decimal number to its binary. So what is the given number given? 4.47. 4.47 is the decimal number. We have to convert to binary. This 4.47 contains two parts. 4 is the integer part. 0.47 is the fractional part. So here we'll go for two processes. First process, converting a integer part and converting a fractional part to binary. Okay, so here we have to go for two steps. First, let us convert integer 4 to integer binary. Second step is convert 0.47 fractional decimal to fractional binary. Okay, so let us take the integer conversion. So here two steps are there. Two steps are there. You can see here. Step number 1. Step number 1 is what? conversion of 4 to binary. 4 is the given integer part of the decimal number. So so for this one, you have to apply successful division method. See, for integer conversion, we have to apply successive division method. For fractional conversion, we have to apply by successive multiplication method. Okay, so I'm repeating once again. For converting a integer decimal number, we have to divide the given integer decimal number with 2 successively. So for converting the fractional decimal number to fractional binary, you have to multiply the given fractional number with the required base, that is 2. So here let us go to step number 1. What is the step number 1? Conversion of 4 to binary. So 4 is the integer part. So here 4 divided by 2. What will be the quotient? 2 2s are 4. That is quotient is 2. What is the remainder? 0. So the first remainder will be the LSB of the required binary number. Let us go to second step in part 1. 2 divided by 2 is how much? Quotient is 1. What is the remainder? 0. Again you take quotient from step number 2. 1 divided by 2, further division is not possible. So therefore I will take quotient as 0. Remainder is 1. Over. You have to stop here because further division is not possible. Final remainder is 1. Further division is not possible. So therefore 1 will be the MSB bit. So first conversion is over. So equivalent binary of integer part of decimal is 100. See, 1 I have written MSB, 0 0 is the LSB. So 100 100. Okay, so this is the first part. Okay, so first part integer conversion 4 to integer binary is 100. So let us move to second part. So what is the importance of second part? Second part we have to consider 0.47. So 0.47 to binary. So 0.47 to the required base. So for this one we are using the successive multiplication by 2 method. So first step that is second in the step 2 I have 3 process or 3 steps. 0.47. So why you have taken 0.47? This is the fractional decimal part. You need to convert. This is a given number. So why you are multiplying by 2? Because this is the required base. Right? The required base is 2. So 0.47 into 2, how much it is? 0.94. So here, this is the product. So this product contains 2 parts. One is integer part, okay, and fractional part. So what is the integer part? 0. So integer part will be the 0. So that 0 will become MSB of the required binary answer. So here, so step number 2. In step number 2, we have to take only fractional part of fractional part of the product in step number 1. So in step number 1, what is the fractional part? So 0.94. So 0.94 into 2, that is equal to 1.88. Again, you separate integer part. So integer part is how much? 1. You take the fractional part of this step in next step. So 0.88 into 2 is how much? 1.76. So integer part is 1. Okay, so integer part is 1. So here, so this will be the LSB bit. So here I will be stopping because see the same steps are repeated. So here, because we got the required number of steps after decimal, we have got here three digits. So here sufficient. So here So binary equivalent binary of fractional part of decimal number is 0.01111. This 0 will be the MSB bit and 1 will be the LSB bit. Okay. So here, so up to what stage you have to multiply, that is important. So successive multiplication method. So you have to keep on multiplying by required base until the fractional part becomes 0. Otherwise, at one stage you will see the repetition in the fractional part. When we see the repetitional, from that stage onwards you stop doing multiplication. Okay, so here I stopped it at the step number 3. So here so so this is the answer of fractional conversion. So finally you have to club these two. So you have to write integer part and fractional part. So final answer can be written as 100 plus 0.011. So 100.011 is the required answer. So in this slide, we'll discuss what is a decimal number system and what is a hexadecimal number system. Decimal number system means it is a familiar number system. So normal in mathematics and all, we are using the decimal number system, which is very familiar to all of them. So here decimal number system is having a base 10. Decimal means 10. So 10 indicates what? It is the base of this number system. So decimal number system has 10 characters or 10 digits from 0 to 9. So hexadecimal number system. What is the base in hexadecimal number system? 16 is the base in hexadecimal number system. So 16 indicates 16 characters or 16 digits in this system. 0 to 9, it is 10 digits, and A to F, it is 6 digits. Okay. In hexadecimal number system, the decimal 10 is written as A, followed by, for 10 we write it as A, for 11 we write it as B, followed in the similar way up to F. That is, for 15 decimal number we write it as F. From 10 to 15 we write A to F. So conversion from decimal number to hexadecimal number. So here we have to convert the decimal number to hexadecimal. So here we have two methods, direct method or indirect method. So direct, what is a direct conversion? So directly I can convert the given decimal number to hexadecimal number by successive division method by required base. Okay, so that will I hope that will be the complicated one. So therefore what I am using, so in the direct method, so given decimal number you successfully divide by 16 in the same way as we divided by 2 in the decimal to binary conversion. So here I want to explain indirect method conversion from decimal to hexadecimal. Okay, so what is the second step? In an indirect method, you need to convert a decimal number to other number system. See here, two possibilities are there. You can convert the decimal number to binary or decimal number to octal. Then again you reconvert from binary to hexa or from octal to hexa by grouping. Okay, so then you can convert to hexadecimal by using grouping from binary number system and converting each octal digits into binary, then grouping and convert these into hexadecimal number. So I will explain the complete theory of this topic in the problem. So here, see here, what is the given here? So here, convert a decimal number 100 into hexadecimal number. So I am going here, I will be using indirect method. So first I will convert the decimal to binary. decimal to binary, and then from binary to hexadecimal. So what is the given number? The given number is decimal number. So what is the decimal number? 100. So 100 you convert to binary. Already we have discussed in the previous slide how to convert a decimal number to binary by successive division by 2 method. So you convert 100 to binary. So what is the answer for conversion? So 11100100 is the answer. So here how many bits are there? So here 1 2 3 4 5 6 7 7 bits are there. So here how to convert this binary to hexadecimal? So hexadecimal. So hexadecimal. So here binary. Okay, already we have seen the conversion from 4-bit binary to hexa. 4-bit binary to hexa. See here, if you see here, start with this LSB bit. Okay, you have to start with LSB bit. You have to move towards left side. Okay, so you have to move towards left side. So this is your LSB bit. LSB bit. You have to move towards MSB, or you start from right side and move towards left side. So you have to group to four group. You have to make grouping of 4 binary digits. So here, so why you have to group 4 binary digits? Because in 8421 we have 4 binary bits. So that is 0 0 1 0. See, 0 0 1 0. So what is the hexadecimal equivalent of this binary number? It is 4. 8421 code. That is in 4 here we have 1. So therefore, so 4 is the equivalent hexadecimal of this number. Then we are write 0 1 1. Okay, you add 1 0 towards MSB side or towards left side. Okay, so because we get 1 bit shortage, so we have to group 4 bits. So in the conversion we have only 3, we are adding 1 extra. So therefore 4 bits are there. So 0 1 1 0 8 4 2, 4 plus 2 is 6. So this is a 6. So therefore what is the final answer? So the given number is the decimal number. What is the given number? 100. 100 is the decimal number. So what is the final answer? 64 is the hexadecimal answer. So 100 decimal is converted to 64 hexadecimal. So this is the binary to hexadecimal. This part will be explained in the next session. How to convert a fractional decimal number to its equivalent hexadecimal fraction. So what are the steps for conversion? So here steps for conversion. So here for converting a fractional decimal number to its equivalent hexadecimal fraction. So here is also, so here what is the, in this slide I will be converting a fractional part. The given number is decimal. Fractional decimal number. Conversion of fractional decimal number to its equivalent fractional hexadecimal number. So let me read out what is given here in this slide. So successive multiplication is used to convert a given fractional decimal number to its equivalent hexadecimal fraction. See, for this conversion, for fractional decimal conversion, we have to apply successive multiplication method. Successive multiplication by required base. So what is the required base? The required base is hexadecimal number system. So therefore, we have to apply successive multiplication method. So here the given decimal fraction is successively multiplied by the base of the target number system. Target means the required base. Okay. So the required base is 16. So during each multiplication iteration, the product generated will have carry and the fractional part. So after each multiplication part, we get one product which contains both integer part and a carry part. Okay, you leave the carry part and you take the you take the fractional part. So here what he is saying, the carry obtained at each multiplication steps becomes a numeral in the hexadecimal fraction. See here, in this step what I told, in this multiplication iteration, after multiplication you get a product which contains integer part and fractional part. So the integer part will become carry as a numeral in the hexadecimal fraction. So here the fractional part of the product is again multiplied by base 16 in the next step. See, in the next step what you should take? You have to take the only the fractional part of the previous iteration method and you have to multiply by 16 in the next step. The process is repeated until the fractional part becomes 0 or the number of multiplication iteration equals the number of digits after the decimal point in the given decimal fraction. Okay, this I will explain when we are discussing the example. So it will become clear for you while we are discussing the example. Weights are assigned for carry obtained at each multiplication step in the increasing order, starting from the first multiplication step to the last step, such that carry obtained in the first multiplication iteration is the MSB after the decimal point and carry obtained in the last multiplication iteration is the LSB bit. Okay, so here, so which is your LSB bit? The carry obtained in the last multiplication step is the LSB bit. The carry obtained in the first multiplication iteration is the MSB bit. So I will explain clearly in the example. See here, this is the problem given to you. So convert, this is example 1. So here the fractional decimal number, I am converting it into fractional hexadecimal number. So here I have taken 4 steps. First multiplication iteration, second multiplication, third multiplication and fourth multiplication. So in the first let us discuss first multiplication method. First multiplication iteration. Multiply 0.0628. This is the given fractional number. Given fractional decimal number 0.0628. You multiply by 16. Why we are multiplying by 16? Because this is the required fractional base. Okay, we are multiplying it by 16. So after multiplication, what we get? We get here 1.0048. This is the product. This product contains 2 parts, integer part 1 as well as fractional part. So here what I am written, fractional part is 0.0048. You separate fractional part from this product and you write carry 1. This is the integer part of this product. Okay. So what I am telling is, the carry obtained in first multiplication iteration will be the most significant digit of the fractional part. So next, coming to the second multiplication iteration. So again 0.0048. So this is the fractional part of step number 1. This is the fractional part of first multiplication iteration. Again I am multiplying it by 16. So if you, when you multiply 0.0048 with 16, you will get again product. So this product again contains fractional as well as carry part. So 0.0768. So 0 will be the carry part and 0.0768 will be the what? Fractional part. Let us take this fractional part in third multiplication iteration. So 0.0768. So 0.0768 is the fractional part of second multiplication iteration. Again multiply by 16. You will get here product 1.2288. 1.2288. Okay. So here fractional part will be 0.2288. Carry part will be 1. So let us go to the fourth multiplication iteration. 0.2288 you multiply by 16. So 0.2288 is the fractional part of third multiplication iteration. So you multiply it by 16, what you will get? 3.6608. This is a product. Fractional part is 0.6608, carry part is 3. So here I will be stopping the multiplication process. Why? Because see here how many digits are given in the question? 0.0628. That means 4 digits are given. That means 4 multiplication iteration is enough. So after the fractional part we got 4 digits. Therefore I will be stopping the multiplication process here. Okay. So the answer for this question is 0.1013. See here 0.1013. So I'll write here like this 0 point, because answer will be after decimal only. 0.1013. 0.1013. So the answer for this one is 0.0628 decimal number converted to hexadecimal number 0.1013. So these are the multiple choice questions which you can answer very easily. So here in this slide I have given 4 MCQs. Okay, so let us discuss one MCQ. The decimal equivalent of hexadecimal number C. C is the hexadecimal number. Okay, so the decimal equivalent of this hexadecimal number. Okay, so A is 10, B is 11, C is 12. C is 12. So therefore, what is the answer? So here we have 13 is wrong one, 10 is wrong, 11 is wrong, and finally, so here for decimal 10 we write A, for decimal 11 we write B, for decimal 10 we write A, for decimal 11 we write B, for decimal 12 we write C. So C is the correct answer. So this is the other MCQs. So these are the references for developing this complete content. Number 1, Digital Fundamentals by T.L. Floyd, and Digital Principles by Malvina and Beach, Principles of Electronics by V.K. Mehta and Rohit Mehta, Digital Electronics by A.P. Godse and Dr. Deepali Godse. So e-resources nwikipedia.org/wiki. Apart from that, I used in internet with Google search. So this is our entire team who helped directly or indirectly for developing this session, for developing this subject completely. So a chairman followed by moderator, followed by subject experts, followed by content developer. So I really thank for the entire team who helped directly or indirectly in developing this e-content of the complete subject. So feel free for any suggestions regarding content developments or tools used in the session or developing the format, etc. So for any suggestions, you can feel free to give suggestions for the to lms.dtech@gmail.com. Thank you one and all.